Okay, we'll get started. Welcome to today's webinar, everyone. Today we'll talk about ANSYS SIwave uh, with its capability on power and signal integrity, coupling with ANSYS Icepak thermal. Uh, so let's get started with SIwave. So first of all, we'll take a look at what is ANSYS SIwave. It's a hybrid full width EM field solver that's finite element method based. It can model printed circuit boards as well as packages. The analyses performed by this tool could be DC analysis with thermal coupling, which is today's topic. And also handles signal and power integrity, both on frequency and time domain, and as well as electromagnetic compatibility and interference. So the general workflow of SIwave is that you have a layout generated in the ECAD system. Either it's from Cadence, Mentor Graphics, Altium, or Zukin, and then you put that in the drawing editor, and then using the and SIwave solver, either it's hybrid 2.5D full wave or uh, either it's hybrid 2.5D full wave um, to tackle to tackle the geometry, and then after that we do a post process, whether it's in DC analysis, AC analysis, resonant modes, or spice models. So in the DC analysis, we have I square R drop, which is current distribution, signal flow graph, coupling with Icepak, and also in AC analysis, we have impedance analysis, S parameter extraction, near and far field extraction, crosstalk analysis, capacitor optimization, and also the spice modes. We have ANSYS, it's ANSYS own Nexium, H spice, Cadence Spectra, P spice, and the Maxwell spice. So and also something to emphasize on is that hybrid solver technology enables simulation of the entire system, either it's on the PCB or the package. So from the plot on this, from the pictures on this page, we can tell the very top picture depicts a near field magnetic field at 778 megahertz. It's a prediction of the EMI on a dual processor quad core PCB. In the middle picture, it's an insertion loss plot for a differential pair. At the bottom, that would be a TDR plot for 8 different signal lines. SIwave supports pretty much all of the prevalent ECAD translations, um, from Cadence Allegro, APD, um, SIP Digital, Virtuoso, Zuken, ODB++, and also other general ECAD formats. So, so in order to do a Icepak thermal coupling, we want to do a DC IR analysis, which is the I square R drop analysis on SIwave. So why is it important to run a DC IR simulation? So first of all, it would supply a clean and sufficient power to today's high-speed semiconductors. It, it will allow more functionality into every integrated circuit is desired. And also, uh, as we enter this this era of ever shrinking um, uh, PCB sizes, it will enable us to operate many different IC functions onto one PCB. So this DCR simulation would help avoiding DC current crowding in planes, traces, and VS, which can lead to PCB failure and a bad circuit performance. It also debugs existing PCB designs, making minor layout changes that result in major performance and reliability improvements. It also reduced, of course, for most of the simulation, the purpose is reduce design swings and also decrease warranty costs associated with thermal cycling issue. The importance of DC simulation. So, uh, oftentimes the failures is lack of good DC design that may not lead to high DC resistance, but it probably cause thermal hotspots due to excessive temperatures and eventual product failure. So the solution to that would be, robust and accurate DC and the PD and design results in a more even spread of current density and reduces risk of failure. So as we can see on the bottom picture here, it's a SIwave, uh, I believe, a current map that's being plotted after doing the DCR simulation. You can see on some of the major components here, you have very high current density, where on those little components, the current are not as high. So when we're talking about DCR simulation, it's often associated with Joule heating. So what is Joule heating? It is it can also be called Joule resistive heating. That is the process by which the passage of electric current through a conductor of electric resistance releases heat. So why do we need to perform such a analysis on putting it on the PCB board? Um, well, first of all, high current PCBs are densely populated with components, um, so it would uh, so would re- so it would reduce the trace and via dimensions if we have a good thermal behavior, um, and because the PCBs current are getting higher and higher today, the current densities would increase. Uh, Thus, higher temperature on some major components, say the battery or uh, the, the the CPU chip. So the Joule heating effects on copper traces causes temperature increases, and thus causes reliability issues, thus causes PCB delamination and failure. So the whole purpose uh, of doing DCR simulation is trying to um, prevent reliability issues and the delamination and failure of the PCB. Um, so for in order to do a DCR simulation, we use the SIwave-DC Solutions. A simple workflow would be, import, setup, and simulate the DC power delivery network. Um, and after you've done so, you can also combine the chip package, and board to perform a system level analysis. So there's a variety of types of DC simulations we can do in SIwave. The first being DCIR drop, which is voltage based. It's for all the nets, including power, ground, and signals. We can also do a DC current distribution. Uh, that the units will be amps per area square, that including the return path. We can also do a DC current magnitude, which tells you the amps into and out of the vias. You could also do power density and total power loss per layer. It can also do automated report generation with user defined pass and fail criteria, and it also enables bidirectional coupling to Icepak for thermal loss simulations. So on the left side on the left picture, it's a voltage drop across a power rail. Um, we can see that in the center of the board, the voltage is relatively higher than uh, the rest of the area. And on the right picture, it's a current distribution across the power rail. Uh, we can we can tell that there's some major hotspot here at this component. this is a voltage drop from power supply to active devices. So we can see at here, it might be it's probably a power source that has the highest voltage. We can by having these kind of power loss map, we can quickly identify high power regions. Um, we can do on the left side, it's only a portion of the whole picture being plotted. On the right side, on the right picture, it's a power loss across all geometry of the board. Um, we can also identify current crowding in copper, and also as we discussed, we can also identify high current vias. Um, we can also generate a table for different element data. As you can see on this column, this indicates whether um, it's whether the test is passed or failed based on the criteria that the users define. It's the via current density check. So you define the criteria for the via current density, and the table would generate itself and tells you whether certain via passes, whether passes or fails the test. Um, this is a metallization current density check, and SIwave-DC automated report that can tells you voltage current limits. It can also provide HTML or PDF format, and it's a layer by layer results. It can also plot the signal flow graph. So it's a fully automated report that will identify path IR drop as well as drop across lumped components along the power rails. It also specifies pass fail criteria for current Joule, voltage drop or across active devices. So this is another representation of the power rail um, for engineers to check whether their designs is valid or not. So multiphysics simulation um, with ANSYS Icepak. So um, once we have a uh, Joule heating, um, once we've done a DCR simulation in SIwave, we can always couple this with our other ANSYS products. So when we have the DC electrical analysis, we pass the Joule heating losses and temperature field into a thermal analysis, which is Icepak, um, and generate the temperature field. Then we check whether the max delta T is greater or smaller than our goal. If it is, um, then we can pass the data into ANSYS mechanical to do a thermal stress analysis, which is deformation. If the max delta T is smaller than is greater than goal, it's not smaller than the goal, then the thermal convergence continues, and then we can have a steady state results. So there's some initial setup in the SIwave to do the DCIR simulation. We want to make sure you check export power dissipation in Icepak format so that you can couple with Icepak. This is some additional illustration of the results. This is a current crowding in traces. Um, so get back to the DC coupling with Icepak. Um, on the SIwave side, we do a board layout file, materials and stack up. Then we set up the file, and things we can control includes match options and voltages and currents, and also materials and stack up. Then we pass the power loss to Icepak thermal, and it can it, it passes back with the temperature information. So, in other words, spatial power loss is transferred to Icepak as a spatial Joule heating map. Then the spatial temperature information is passed from Icepak to SIwave, interpreted as spatial thermal modifiers for electrical conductivity. Um, so starting from release 17.1, SIwave users can quickly and easily set up an Icepak simulation in SIwave. As you can see on the right upper corner, there's a little Icepak icon enabled in SIwave. Things you can do through SIwave for Icepak, including conduction only or convection, airflow inside enclosure, component power dissipation, and also enclosure size. So once you decide to do to to adapt this workflow, the simulation runs completely inside SIwave. No Icepak GUI interaction is required. It, by doing so, allows electrical engineers to quickly estimate board temperatures. Um, so um, once we have a Icepak simulation running SIwave, we can have a temperature map uh, exported from Icepak to into SIwave. So this is pretty much it for the slides. I will I'll briefly show you some show you what I mean by those slides. So here we have a general PCB board with multiple layers. The simulation is already being performed, so no no setups need to be done. We're just taking a look. We're just taking a look at the results. So as you can see here, uh, I have a DCR simulation done, and as well as Icepak simulation. So if we take a look at it, um, now it's showing you the current density. We can we can check all of them, so this map will be very colorful, very satisfying to look at. Might not be as informative as it should be. So we check off some of the options. Just looking at first, we can look at the current through the vias. It will tells you uh, which via has a higher current, which via has a lower current. We can also check current density, where you can see how the current generally flows on every layer to make it um, more more friendly to our eyes. Um, oh, okay. We check this layer. We uncheck all of them. Let's just do one layer. So we check off this. So on this layer, we can see there's not much return path on this layer, but still we can see that at this on this net there is a very heavy current flow. We can also do so as it is, the voltage is also pretty high on this component. And if we turn on the power, it shows you that here is where you should be concerned at. Um, once we have this DCR simulation, we can, as we discussed in the slides, we can pass it to Icepak and do Icepak simulation. Once the Icepak simulation is done, we can display temperature on this geometry. So do you remember where the power was pretty high? So it's the same as we anticipated. It's in the middle area. Um, we could also, from this, we could also view the profile. Um, we can also export the report as the HTML. We can also, you know, view the simulation properties, etc. Um, so yeah, this is pretty much it in terms of introducing this thermal coupling with Icepak. Um, does anyone have any question? If I'll wait for any questions here. If you have any questions, you can type in here in the chat. Okay. It doesn't seem to have any problems from anyone. So if you're so if you don't have any questions, this will be end of this webinar. Feel free to contact Ozen Engineering um, for for any new information on the latest release. We have 2019 R1 release recently, and also Ozen Engineering will be having an open house tomorrow. So if any of you guys are available and interested, we'll welcome you in our office. It will be 11 to 2 p.m. Lunch will be provided, and we'll talk about some ANSYS. Uh, okay. Well, this is it for the webinar. Thanks for attending. Thanks for attention. Bye.